A single photon can cross billions of light years, bend around galaxies, pass through darkness older than the sun, and end its journey in one silent flash inside a human eye. Yet during that immense passage, it behaves neither fully like a particle nor fully like a wave. It carries energy without rest mass, travels through fields rather than empty nothingness, and follows rules that seem to change the moment it is measured. Light reveals nearly everything in the universe, while remaining one of reality's deepest mysteries. A quiet like a subscription or a share helps this kind of calm science storytelling reach more curious minds. Sincere thanks for spending this time with the video. Listeners are warmly invited to leave a comment with the local time and the place where this journey is being heard or watched. Now, the path opens from ancient starlight to quantum fields as the true nature of light begins to unfold. Long before the first star burns, before any planet gathers from dust, and before darkness has meaning, the universe is filled with light. It is not the gentle light of a sunrise or the narrow beam of a distant star. It is a restless sea of radiation trapped inside matter, scattered again and again by charged particles moving through an expanding furnace. In these earlier stages, space is not transparent. A photon cannot travel far before striking an electron, vanishing into one interaction and reappearing in another. Light exists everywhere, yet no clear ray crosses the cosmos. The universe glows, but it cannot be seen through. Its radiance is imprisoned within the hot plasma from which everything else is slowly emerging. This condition lasts for hundreds of thousands of years. The universe expands, and expansion cools it. Temperatures fall from unimaginable extremes toward a threshold at which a simple but decisive change becomes possible. Electrons, once moving too violently to remain attached to atomic nuclei, begin to settle. Protons capture electrons, neutral hydrogen forms. Helium is already present, forged in the first minutes, but now the cosmos gains stable atoms in vast numbers. The transformation is quiet compared with the violence that comes before it, yet its consequence is immense. Free electrons have been scattering light constantly. Once many of those electrons become bound inside atoms, the universe suddenly becomes transparent. Photons that have been trapped in the plasma are released into open space. Their paths lengthen. Their last scattering events become the beginning of journeys that continue across almost the entire age of the universe. The light from that transition still exists. Cosmic expansion stretches its wavelength until it no longer appears as visible light. It now fills space as microwave radiation, arriving from every direction with nearly the same faint temperature. Modern instruments call it the cosmic microwave background, but it is more than a background. It is a surviving surface of ancient light, a record from the moment when the universe first becomes transparent. Every point in the night sky carries some trace of it. Behind stars, behind galaxies, behind the luminous structures of later cosmic history, this old radiation remains. It is the nearest view of the young universe that light allows. Before that surface, matter and radiation are so tightly coupled that ordinary telescopes cannot look deeper. The early cosmos is hidden not because it is dark, but because it is too bright and too opaque. A photon released at that ancient boundary does not move through a static emptiness. Space itself expands as the photon travels. Its wavelength grows with that expansion. Light that begins at a shorter, more energetic wavelength becomes steadily redder, then slips beyond the range of human vision, then continues into the microwave part of the electromagnetic spectrum. The photon loses energy as measured by observers carried apart by the changing geometry of the universe. Nothing along its route needs to touch it. The changing scale of space is enough to alter how its frequency is received. This cosmic redshift is not merely a fading of colour. It is a signature of an evolving universe, written into the light that crosses it. Yet the photon carries no awareness of the immense transformation unfolding around it. Soon after the universe becomes transparent, a long, dim era begins. Matter exists, radiation exists, and gravity quietly deepens small differences in density, but no stars yet shine. The cosmos enters what is often called the Dark Ages. The name is slightly misleading, because ancient radiation still fills all space. What is absent is new visible light from stars. Hydrogen and helium drift through expanding darkness, while gravity gathers them into denser regions. Tiny irregularities, present from the early universe, become the seeds of larger structures. Over millions of years, gas collects within the gravitational wells of dark matter. The first stars eventually ignite. They are likely massive, short-lived, and chemically simple, born from material containing almost no elements heavier than helium. Their light floods the surrounding gas. Their ultraviolet radiation tears electrons away from atoms, gradually changing the state of matter across enormous regions. Their deaths scatter newly forged elements into space: carbon, oxygen, silicon, iron, and other ingredients of later worlds begin to enter the cosmic mixture. Even the apparent straightness of its motion depends on the shape of space-time. Near matter, gravity does not pull light as though it were a small stone. Instead, mass and energy curve the geometry through which light moves, and the photon follows that curvature. Across the young universe, these deflections are slight, but over cosmic ages they help turn galaxies and clusters into natural lenses, allowing later observers to detect structures that would otherwise remain hidden. The original photon continues through this changing universe. It passes regions where no stars exist and regions blazing with young galaxies. It may travel through expanding voids, across filaments of matter, near clouds of gas, or past gravitational structures that slightly bend its route. Most photons do not enjoy such uninterrupted passage. Many are absorbed, scattered, redirected, or transformed. Light crossing dust may warm tiny grains. Light striking an atom may raise an electron to a higher energy state. Light meeting free-charged particles may change direction. High-energy photons may trigger more violent interactions. But some photons move for billions of years without being absorbed. Their survival is not a sign of endurance in the ordinary sense. A photon does not wear down through distance alone, in empty space. It does not lose energy by friction, because there is no substance rubbing against it. Its energy may be redshifted by cosmic expansion, and its path may be curved by gravity. But the photon itself does not gradually decay simply because the journey is long. This is one reason light becomes the great messenger of astronomy. Matter usually moves slowly compared with cosmic distances. Light crosses those distances at the universal speed limit, carrying information from places no spacecraft can reach. The surface of a star, the atmosphere of a planet, the gas around a black hole, and the remains of an exploded sun all leave marks on passing radiation. Wavelengths reveal temperature. Spectral lines reveal chemical elements. Polarization reveals orientation and magnetic structure. Changes in brightness reveal motion, rotation, eclipses, and violent events. Nearly everything known about the distant universe arrives in this form. Astronomy is built from intercepted light. A detector does not receive the object itself. It receives photons that have interacted with the object, escaped, crossed space, and finally surrendered their energy inside an instrument. The photon's arrival is therefore also its end. When it strikes a detector, it may transfer energy to an electron, producing a measurable signal. The light is not stored as a tiny glowing bead. Its energy becomes part of the detector. An event that begins near the birth of cosmic transparency may finish inside a machine built on a small planet billions of years later. This image is powerful, but it also invites a misleading question. It is tempting to ask what the photon experiences during the journey. Relativity makes that question delicate. Massive objects can carry clocks, and the time measured along their paths is called proper time. Light follows a different kind of path through space-time, one for which the proper time between emission and absorption is 0. But there is no valid rest frame of a photon. No observer can move alongside light and describe the universe from its viewpoint. Statements claiming that a photon sees no time are therefore useful only as careful shorthand. They point toward the geometry of light-like motion, not toward a hidden consciousness or an actual clock carried by light. The deeper mystery remains intact without giving the photon human qualities. Between emission and absorption. What is light? Is it a particle moving along a line, a wave spread through space, an excitation of a field, or something that refuses every familiar category? The ancient photon already contains the whole problem. It leaves one interaction and arrives at another. It carries energy and momentum. It spreads according to wave equations. It can interfere with alternatives. It can be counted one event at a time. The long history of physics grows from attempts to understand how all these statements can be true together. The first transparent light of the cosmos therefore does more than illuminate the early universe. It opens a path into the nature of reality itself. The journey begins in plasma, continues through darkness, and ends in a detector. But the true question lies between those endpoints, in the strange rules that govern light while it crosses the silent distance. For most of human history, light is known through its effects rather than its nature. It reveals shape, distance, colour, motion, and texture. Yet it does so without offering any obvious clue about what it is. A stone can be held, water can be poured, wind can be felt against skin. Light seems different. It arrives without weight, fills a room without accumulating, and vanishes the instant a flame is covered, because sight feels immediate. The earliest explanations often begin with the eye itself. Some ancient thinkers imagine vision as an active process in which something leaves the eye, reaches outward, and touches the world. In this view, seeing resembles a kind of invisible contact. The idea has an intuitive appeal. Attention feels directed. A gaze seems to move from observer to object, yet darkness exposes a weakness. If sight depends only on rays sent outward by the eye, then objects should remain visible even without a lamp, a fire, the moon, or the sun. They do not. Something external must take part. Other thinkers therefore argue that objects release forms, images, or fine material traces that travel inward toward the eye. This reverses the direction, but preserves the deeper assumption that sight requires something to cross the space between object and observer. The argument begins before experimental science exists in its modern form, but it already contains the central puzzle. Vision depends on a messenger. The difficulty lies in identifying the messenger and discovering the rules that govern its motion. Greek natural philosophy offers several competing answers. Empedocles describes a relationship between fire within the eye and light outside it. Plato gives vision a combined structure in which visual fire meets daylight. Aristotle rejects a simple stream of particles and instead treats light as a condition made actual in a transparent medium. Euclid approaches the matter geometrically. His interest is less in the substance of light than in the paths associated with sight. Straight lines extending from the eye can explain perspective, apparent size, and the way objects align within a field of view. This geometric method proves powerful even when its physical assumptions are uncertain. It establishes a lasting lesson. Light may be understood by tracing paths. A ray is not necessarily a tiny physical thread. It is a mathematical line indicating direction. Once this abstraction appears, reflection can be studied with precision. A polished metal surface or still pool sends light away in an orderly manner. The angle at which a ray approaches a surface matches the angle at which it departs. The rule is simple, but its implications are broad. Mirrors form images because many reflected rays follow a consistent geometry. Curved mirrors can concentrate light or spread it apart. The behavior is regular enough to support calculation, and regularity invites experiment. Yet geometry alone does not answer what travels along the ray. It describes the route while leaving the traveller obscure. Over centuries that gap remains. The study of light advances through observation, craftsmanship, and mathematics, often in places where astronomy, medicine, and instrument making meet. Glassmakers learn that curved transparent surfaces enlarge or distort. Physicians examine the anatomy of the eye. Astronomers depend on accurate sighting. Builders use shadows to measure height and direction. The practical uses of light steadily deepen the theoretical mystery. A crucial change comes through scholars working in the Islamic world, where Greek texts are translated, criticized, and expanded. Among the most important figures is Ibn al-Haytham, known in Latin traditions as Al-Hazan. He approaches vision not as a problem to be settled by inherited authority, but as a subject for controlled investigation. The eye, in his account, does not send rays outward. Light travels from luminous sources, reaches objects, reflects from them, and then enters the eye. This may seem ordinary now, but it reorganizes the problem. Sight becomes a physical chain of events. A source emits light. A surface redirects part of it. The eye receives it. Vision follows from incoming radiation rather than an outward act of perception. Ibn al-Haytham studies reflection, refraction, shadows, colour, and the geometry of image formation. He uses dark chambers with small openings to examine how rays cross. Light from different parts of an outdoor scene passes through a narrow aperture and forms an inverted image on an interior surface. The effect later becomes associated with the camera obscura, but its deeper significance lies in what it shows about propagation. Rays from separate points travel independently along straight paths. They can cross without colliding or becoming confused. The image turns upside down because the ray from the top of an object continues downward after passing through the opening, while the ray from the bottom continues upward. The room becomes a quiet demonstration that light has structure before it reaches the eye. Refraction introduces a subtler problem. When light passes from air into water or glass, its direction changes. A straight stick partly submerged appears bent. A coin at the bottom of a bowl seems displaced from its true position. The surface does not merely reflect light, it changes the path of transmitted light. This bending suggests that the surrounding material influences propagation. The effect is consistent, but not immediately simple. The amount of bending depends on the materials and on the angle at which the light arrives. For centuries, scholars seek a general rule. Ptolemy measures refraction. Ibn Sal develops a mathematical relation for the bending of rays in lenses and burning mirrors. Later, European work gives the relation the form now commonly associated with Snell and Descartes. The rule links the incoming and outgoing angles through a property of the materials. It allows lenses to be designed rather than merely discovered by trial. Once the path of light can be predicted, glass becomes an extension of human vision. Spectacles correct focusing errors. Magnifying lenses reveal fine structure. Telescopes bring distant moons into view. Microscopes uncover living worlds too small for unaided sight. Each instrument confirms that light obeys stable laws, yet each also complicates the question of what light must be. Reflection makes it seem like a stream that bounces. Refraction makes it seem responsive to the medium it enters. Colour adds another layer. White sunlight passing through glass can spread into a band of colours. Rain droplets divide daylight into a rainbow. Thin films of oil or soap produce shifting hues. Crystals split images. Certain transparent materials transmit light differently depending on orientation. None of these effects fits comfortably into a single early picture. Light behaves with a kind of discipline, but its discipline has many forms. The eye itself contributes further complexity. It does not passively record the world with perfect accuracy. The curved cornea and lens focus incoming light onto the retina. The image forms inverted, yet perception does not present an upside-down world. The pupil controls the amount of light entering. The retina responds differently across wavelength and brightness. The brain builds continuity, depth, colour, and motion from electrical signals. Ancient debates about whether sight begins in the eye or outside it therefore contain a partial truth on both sides. Light must arrive from the world, but seeing is not complete until the nervous system interprets what arrives. The external path and the internal response are inseparable parts of vision. Though they are not the same phenomenon, by the beginning of the scientific revolution, the study of optics is poised between successful geometry and uncertain ontology. Rays can be traced, angles can be measured, lenses can be polished to gather light from distant objects, mirrors can be shaped to concentrate it, yet the central question remains untouched. A ray explains where light goes, not what light is. Is it a stream of tiny bodies moving through space? Is it a disturbance travelling through some invisible substance? Is colour carried as separate kinds of light, or created when white light is altered by matter? Does light move instantaneously, or does it require time to cross a distance? Every improved instrument makes the mystery sharper. The telescope reveals that celestial bodies obey the same optical rules as objects on Earth. The microscope shows that living tissue becomes visible only because light is redirected through glass and into the eye. The same phenomenon links the smallest structures to the farthest visible worlds. Light becomes the thread joining scale to scale, yet the thread itself remains hidden. This is the ancient question carried into modern science, not merely how sight works, but how reality becomes visible at all. The answer begins to divide into rival visions. One treats light as a procession of particles, the other treats it as a wave. Both will explain something essential, neither will survive unchanged. By the late 17th century, the study of light stands at a crossroads. Geometry has mapped the paths of rays with remarkable success. Lenses are opening new windows onto the heavens and the microscopic world, and experiments with prisms are revealing that white light contains a hidden spread of colours. Yet the nature of light remains unsettled. Two broad possibilities compete. Light may consist of tiny bodies moving through space, striking surfaces, passing into glass, and entering the eye. Or light may be a disturbance, a wave travelling through some medium that fills the world. Both ideas can explain part of what is observed. Both also leave difficulties. The argument becomes more than a dispute over terminology because it touches the deepest picture of nature. If light is made of particles, then vision depends on a stream of minute projectiles. If light is a wave, then empty space may be filled with an invisible substance capable of carrying oscillations. Into this uncertainty comes Isaac Newton, already transforming mathematics and mechanics. His authority will shape the debate for generations. Newton studies sunlight with prisms and discovers that the colours of the spectrum are not created by glass. They are already present within white light. A second prism can recombine them into white again, and a carefully chosen coloured ray keeps its colour after further refraction. This leads Newton to argue that different colours correspond to different kinds of light, each bent by a different amount when passing through glass. The result is one of the great achievements of optics. It explains why ordinary lenses produce coloured fringes and why a rainbow separates sunlight from red to violet. Yet Newton's interpretation remains particle-like. He imagines light as corpuscles, extremely small entities emitted by luminous bodies and travelling rapidly along straight lines. Their paths explain sharp shadows, their impacts explain reflection. Their interactions with matter might explain refraction. The model feels compatible with the mechanics he's building for planets, falling objects, and collisions. Nature, in this view, is governed by forces acting on bodies. Light can be brought into the same framework. Reflection appears simple. A corpuscle approaches a smooth surface and rebounds, much as a small ball might bounce from a wall. The equal angles of arrival and departure follow naturally from the geometry of the collision. Refraction is more difficult. But Newton proposes that matter exerts a force on light near the boundary between two materials. As a corpuscle enters glass or water, it is pulled toward the denser medium. Its motion changes direction, and the ray bends. This picture predicts that light should move faster in denser transparent materials because the attractive force accelerates the corpuscles. At the time, the speed of light inside glass cannot be measured accurately enough to test the prediction. The weakness remains hidden. Newton also knows that light displays patterns more complicated than simple bouncing and bending. When a curved lens rests on a flat glass plate, rings of colour appear around the point of contact. These patterns, now called Newton's rings, resemble the repeated bright and dark bands expected when waves overlap. Newton records them carefully, yet he does not abandon corpuscles. Instead, he suggests that light particles pass through alternating states that make them more likely to be reflected or transmitted. He calls these tendencies fits of easy reflection and easy transmission. The idea preserves the particle model, but it adds an unexplained rhythm to each corpuscle. Light begins to look particle-like in travel and wave-like in repeating behaviour, though quantum duality still lies centuries away. At nearly the same time, Christian Huygens develops a different account. For Huygens, light is a wave moving through an all-pervading medium. Every point reached by a wave becomes the source of smaller secondary waves, and the advancing surface of the combined disturbance forms the next wavefront. This principle gives a geometric method for predicting how light moves. Straight propagation emerges because the secondary waves combine to advance the front forward. Reflection follows because the wavefront meets a surface and turns according to the known angular rule. Refraction follows because the wave changes speed when it enters a new medium. One side of the wavefront slows before the other, causing the whole front to rotate and the ray to bend. Huygens reaches a conclusion opposite to Newton's. Light should move more slowly in denser transparent materials, not faster. Much later, measurement will support Huygens. The disagreement becomes a clear experimental divide, but the necessary instruments do not yet exist. Robert Hooke also favours a wave-like view. His studies of thin films, colours, and microscopic structures suggest rapid vibrations. He and Newton clash over credit, interpretation, and authority. Their dispute is personal, but the larger conflict is conceptual. Hooke sees pulses travelling through a medium, while Newton resists the claim that glass creates colour by modifying pure light. Newton is right that white light is a mixture of colours, yet Hooke and Huygens are closer to the later understanding of interference and propagation. Each side grasps a different part of the phenomenon. Newton's corpuscles reflect the discrete localized character that light will later display in quantum experiments. Huygens' waves anticipate the mathematics of diffraction, interference, and polarization. But these future reconciliations are invisible. The models appear mutually exclusive. Light must be one thing or the other. Newton's influence gives the particle theory a powerful advantage, especially in Britain. His broader successes make his judgments difficult to challenge. The same mind that describes universal gravitation develops new mathematics and explains celestial motion now presents a detailed theory of light. The theory is not accepted merely because of personality, but reputation affects which questions seem settled and which alternatives receive attention. Corpuscles also fit the mechanical philosophy of the age. Waves are known in water and air, but every familiar wave requires a material carrier. Sound cannot cross a vacuum because it needs matter to compress and expand. Water waves require water. If light is a wave crossing the emptiness between the sun and earth, something must be waving there. The proposed answer is the luminiferous ether, an invisible medium filling space. Yet this substance must be thin enough for planets to move through without resistance, and rigid enough to carry light at enormous speed. It must fill every region while remaining undetected. The ether solves one problem by creating several more. Newton recognizes these difficulties, although he sometimes considers subtle media in his own speculations. The absence of a convincing wave carrier strengthens the particle case. Another difficulty for wave theories comes from the apparent straightness of light. Sound bends around corners, water waves spread around obstacles. Light usually forms sharp shadows and seems unwilling to curve into sheltered regions. If light is a wave, why does a wall block vision while voices remain audible around it? Newton treats this difference as strong evidence for corpuscles. The answer depends on scale. Diffraction is most noticeable when an opening or obstacle is comparable to the wavelength. Sound has wavelengths large enough to bend around doors and buildings. Visible light has wavelengths far smaller than everyday objects, so its bending is usually subtle. But no one in Newton's time knows the wavelength of visible light with modern precision, and the small diffraction effects already observed are not yet woven into a decisive theory. Francesco Maria Grimaldi has described the spreading of light near edges and introduces the term diffraction, but the phenomenon still appears as a slight failure of rays rather than a signature of waves. Polarization creates another challenge. Certain crystals split light into two rays, and transmitted brightness can depend on orientation. A simple wave, like sound, struggles to explain this directionality. Huygens offers a construction for double refraction, but lacks the later concept of transverse electromagnetic waves. Newton's particles can be assigned hidden orientations, yet this too is incomplete. The evidence refuses to line up neatly behind either camp. Light moves in straight rays, bends at boundaries, reflects from surfaces, separates into colours, forms rings, spreads near edges, and changes with orientation. Each observation reveals a different face. By the time Newton publishes his major work on optics in the early 18th century, the corpuscular picture dominates, but it does not close the mystery. It organizes experiments and offers mechanical explanations, yet unresolved patterns remain beneath its surface. The wave theory survives, waiting for an experiment simple enough to expose what particles cannot easily imitate. That experiment will not require a distant star, an elaborate telescope, or a powerful machine. It will require only a source of light, two narrow openings, and a screen where darkness and brightness arrange themselves into a pattern that changes the argument forever. A narrow beam of light approaches two small openings cut into a barrier. Beyond them waits a screen. If light consists only of tiny particles moving along definite paths, the expectation seems simple. Each particle should pass through one opening or the other, and two bright regions should appear behind the slits. Yet the screen does not show two clean bands. It fills instead with a sequence of bright and dark stripes, evenly spaced and gradually fading toward the edges. Light reaches some places strongly, weakly reaches others, and avoids certain regions almost completely. The pattern is the signature of interference, the same kind of addition and cancellation found when waves meet on water. Where two crests arrive together, the disturbance grows. Where a crest meets a trough, the disturbances cancel. Brightness and darkness are no longer merely the presence or absence of straight rays. They emerge from the relationship between overlapping waves. This experiment becomes closely associated with Thomas Young in the early 19th century, though the underlying idea develops through earlier observations of thin films and diffraction. Young's achievement lies in making the wave behavior of light difficult to dismiss. He allows light from a common source to reach two narrow openings, creating two related wave trains. Because the waves begin with a stable relationship, they can combine predictably at the screen. A point where the paths differ by a whole number of wavelengths receives waves in step and becomes bright. A point where the path difference places crest against trough becomes dark. The pattern gives light a measurable wavelength, an astonishingly small distance far below ordinary human perception. Different colours produce different spacings because their wavelengths differ. Red light forms wider bands than blue light. Colour, in this wave picture, is connected not to separate kinds of corpuscles alone, but to the rhythm of an oscillation. The result does not merely favour waves, it reveals that darkness can be created by adding light to light. Two beams that illuminate a region separately can cancel there when combined in the right phase. This seems strange only if brightness is imagined as a pile of luminous particles. For waves, cancellation is natural. The energy does not disappear from the entire pattern. It is redistributed, strengthening bright regions while weakening dark ones. The screen records a geometry of possible paths, a map of how phase relationships guide where energy is likely to arrive. Interference also explains the colours that appear in soap bubbles, oil films, and thin layers of transparent material. Light reflects from the front and back surfaces of the film. The two reflected waves travel slightly different distances before meeting. Some wavelengths return in step and become stronger. Others return out of step and weaken. As the film thickness changes, the favoured colours change. A drifting surface therefore carries bands of colour that shift with angle and thickness. Newton studies related rings without accepting a full wave account, but the interference model gives the recurring pattern a direct cause. The colours are not painted into the film. They arise from the meeting of light with itself. Diffraction extends the evidence. When a wave encounters an opening, it does not always continue as a perfectly narrow beam. It spreads. The amount of spreading depends on the relationship between the opening and the wavelength. A wide doorway barely alters a small wave, while a narrow opening forces the emerging wave to fan outward. Visible light has such short wavelengths that ordinary openings appear enormous by comparison, so its diffraction is often subtle. But when light passes a fine edge, a narrow slit, or a tiny obstacle, the spreading becomes measurable. Instead of a sharp boundary between light and shadow, delicate fringes appear. Bright and dark bands occupy regions where simple ray geometry predicts smooth illumination or complete darkness. Augustin Jean Fresnel develops the mathematical wave theory needed to describe these effects in detail. He treats a wavefront as a vast collection of secondary contributions, extending the principle associated with Huygens. Every small part of the wavefront contributes to what happens farther ahead. Their phases differ because their paths differ. At each destination, the contributions add or cancel, Straight-line propagation survives as an approximation because contributions away from the forward direction often cancel one another. Near an edge or opening, that balance changes, and the hidden wave structure becomes visible. Fresnel's theory predicts patterns with remarkable precision, but it initially faces resistance. The particle picture still carries Newton's prestige, and the wave theory appears to depend on an undetected ether. During a scientific competition in France, Simeon Denis Poisson examines Fresnel's equations and identifies what seems to be an absurd consequence. If a small circular obstacle blocks a beam, the wave calculation predicts a bright point at the center of the shadow. Contributions bending around every part of the circular edge should arrive there in phase. A particle theory suggests darkness at the center. The prediction appears so unreasonable that it is offered as evidence against Fresnel. Yet experiment reveals the bright point. A luminous spot appears inside the geometric shadow, exactly where the wave theory places it. The result becomes known by several historical names, but its meaning is clear. Light reaches the center not by passing through the obstacle, but through the combined effect of waves spreading around it. Shadow itself contains structure. The victory of the wave theory grows stronger, though one major puzzle remains. Waves can oscillate in different ways. Sound in air is mainly longitudinal. The motion of the medium lies along the direction the wave travels, producing compressions and expansions. Water waves have more complicated motion, but their visible rise and fall suggests another possibility. Light displays polarization, a behavior that requires direction within the oscillation. Certain crystals divide a beam into two. Reflections from glass or water favor particular orientations. Sheets made from aligned molecules can transmit one orientation while blocking the perpendicular one. When two polarizing filters are aligned, light passes. When one turns through a right angle, the transmitted light can nearly vanish. The beam has not simply become weaker in every direction, it carries an orientation. This forces wave theory to change. A purely longitudinal wave cannot easily account for polarization because it has no sideways direction to select. Fresnel and others developed the idea that light is transverse, meaning the oscillation lies across the direction of travel. A transverse wave can vibrate along one sideways axis, another axis, or a combination of both. Polarization describes that orientation. The concept explains why crystals and filters respond differently as they rotate. It also creates a severe demand on the supposed ether. A medium that carries transverse waves usually behaves as though it has rigidity, because sideways displacement must be restored. Yet the ether is also expected to fill space without slowing planets. It must behave like an extraordinarily stiff substance for light, while offering no detectable resistance to matter. The wave theory succeeds experimentally but inherits an increasingly unnatural carrier. Still, by the middle of the 19th century, interference, diffraction, and polarization form a united body of evidence. Light spreads, overlaps, cancels, reinforces, bends around boundaries and carries transverse orientation. Ray optics remains useful. Just as a map remains useful without showing every grain of soil. Rays describe the average direction of propagation when obstacles and instruments are much larger than the wavelength. Wave optics reveals what the ray approximation hides. A sharp image, a narrow shadow, or a focused beam is never infinitely precise. Diffraction imposes a limit. A lens cannot focus light into a perfect point because waves spread. A telescope cannot distinguish arbitrarily close stars because its aperture creates a diffraction pattern. A microscope cannot resolve structures far smaller than the wavelength it uses without special methods. The wave nature of light therefore sets boundaries on observation itself. It determines how finely reality can be seen through ordinary optical instruments. Yet the triumph is incomplete. The theory describes how light travels, but not finally what is oscillating. The ether remains hypothetical, and its required properties grow stranger with every success. More importantly, later experiments will show that even the wave picture cannot explain how light exchanges energy with matter. A faint beam can arrive as separate detection events. An electron can receive energy in a sudden packet rather than through a continuous wash. The interference pattern is unmistakably wave-like, but each mark on a detector is localized. Light spreads as though it explores many paths, then arrives as though only one event occurs. The old conflict is not resolved by choosing waves over particles. It is only deepened. Interference reveals a structure richer than either classical category, and the dark bands on the screen become openings into a reality where possibilities combine before outcomes appear. By the middle of the 19th century, the wave nature of light appears secure, yet the central question remains unanswered. Water waves require water, sound waves require air, stone, or some other material that can compress and expand. Light crosses the emptiness between the sun and earth, passes through the darkness between stars, and continues through regions where matter is almost absent. If light is a wave, then something must be changing as the wave moves. The proposed ether is meant to provide that hidden substance, but no experiment reveals it clearly, and its imagined properties become increasingly unnatural. A different path opens through the study of electricity and magnetism. These forces seem separate at first. Electric charge can attract or repel. A magnet can turn a compass needle and pull iron without visible contact. Yet experiments begin to show that the two are linked. An electric current flowing through a wire produces a magnetic effect around it. A changing magnetic field can drive electric current through a nearby circuit. Motion, charge, and magnetism form a connected system, though the connection is still expressed through scattered laws and special cases. James Clerk Maxwell gathers these pieces into a single mathematical structure. His achievement does not begin with light. It begins with an attempt to understand how electric and magnetic effects spread through space. Earlier physics often treats forces as acting across distance, with one object influencing another without a visible mechanism between them. Michael Faraday offers a different picture. He imagines lines of force extending through the region around charges and magnets. These lines are not merely geometric aids. They suggest that space itself carries a physical state. A charge changes the electric condition around it. A current changes the magnetic condition. Another object responds not directly to the distant source, but to the field present at its own location. Maxwell translates this visual and experimental intuition into equations. The field becomes more than a metaphor. It becomes something that can store energy, change with time, and influence matter. One relation describes how electric charge produces an electric field. Another expresses the absence of isolated magnetic poles in ordinary electromagnetism, meaning magnetic field lines form continuous loops rather than beginning or ending on a lone magnetic charge. A third captures Faraday's discovery that a changing magnetic field generates an electric field. The fourth begins with the fact that electric current produces magnetism, but Maxwell recognizes that the existing form is incomplete. A changing electric field must also create a magnetic field, even where no ordinary current flows. This added term, later called displacement current, closes the structure. Without it, the equations fail in situations such as the space between the plates of a charging capacitor. With it, electricity and magnetism become parts of one self-consistent whole. The consequence is profound. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. If a disturbance begins in one, it can sustain itself through the other. The electric change produces a magnetic change nearby, which produces another electric change farther on, and the coupled pattern moves through space. No material substance needs to carry it in the way air carries sound. The electromagnetic field itself is what changes. Light no longer requires a mechanical ether as its obvious foundation. The wave is a travelling pattern in electric and magnetic fields. Maxwell examines the speed predicted by his equations. The result depends on measured electrical and magnetic properties of empty space. When these values are combined, the calculated speed is astonishingly close to the known speed of light. The agreement is too precise to dismiss. Light, Maxwell concludes, is an electromagnetic disturbance. Optics, electricity, and magnetism are not separate branches of nature. They are different views of the same phenomenon. A beam of visible light consists of oscillating electric and magnetic fields, oriented across the direction of travel and linked to one another. The fields rise, fall, reverse, and repeat as the wave advances. The electric field does not push the magnetic field from behind, and the magnetic field does not trail as a separate companion. They form one unified electromagnetic structure. The wave moves through vacuum at a fixed speed determined by the laws themselves. This is a major change in the meaning of empty space. A vacuum is not merely a blank absence. It can support fields. It can contain energy. It can carry a disturbance across cosmic distance without the transport of ordinary matter. The old question about what is waving receives a new answer. No hidden fluid needs to ripple. The electromagnetic field is the changing entity. Matter creates disturbances in the field, and matter responds when those disturbances arrive. An accelerating electric charge is one source of electromagnetic radiation. An electron moving steadily in a straight line does not radiate in the same way, but an electron that oscillates, curves, or changes speed disturbs the surrounding field. The disturbance travels outward. Inside a radio antenna, electrons are driven back and forth, producing waves with long wavelengths. Inside a hot object, charged particles move and collide, emitting a broad range of radiation. Inside an atom, the quantum description will later replace the classical picture, but the connection between changing charge systems and emitted light remains central. At the receiving end, electromagnetic waves push on charged particles. The electric component drives electrons in matter. In an antenna, this motion becomes an electrical signal. In the retina, light triggers molecular changes that begin the process of vision. In a solar cell, absorbed radiation frees charge to move through a circuit. Emission and absorption are two sides of the same coupling between matter and the electromagnetic field. Maxwell's theory also explains why light is transverse. The electric and magnetic fields oscillate sideways relative to the direction of propagation. This gives light an orientation, and therefore a natural account of polarization. A polarizing material responds more strongly to one direction of electric oscillation than another. Two aligned filters allow a component of the field to pass. When their axes become perpendicular, the second filter blocks what remains. Polarization no longer appears as an awkward addition to wave theory. It follows from the geometry of electromagnetic fields. Reflection and refraction also gain deeper meaning. When an electromagnetic wave reaches matter, its electric field drives charges within the material. Those charges respond and produce their own fields. The combined behavior of the incoming wave and the induced response creates reflected and transmitted waves. In a transparent medium, the collective interaction delays the propagation compared with vacuum, so light travels more slowly through glass or water. The wave bends at a boundary, because different parts of the wavefront change speed at different moments. Huygens' geometrical construction now rests on an electromagnetic foundation. Newton's prediction that light should speed up in a denser transparent substance, is replaced by the opposite result. The theory is powerful enough to suggest more light than human eyes can detect. Maxwell's equations do not require one special wavelength. They permit electromagnetic waves across a continuous range of frequencies. Visible colours occupy only a narrow band. Waves with longer wavelengths should exist, as should waves with shorter wavelengths. Heinrich Hertz later produces and detects long electromagnetic waves in the laboratory. Sparks in one apparatus create oscillations, and a separate loop responds across open space. The waves reflect, interfere, and form standing patterns just as Maxwell predicts. They are invisible, but they behave as light. Radio communication eventually grows from this discovery, carrying signals through air and vacuum. Other regions of the electromagnetic spectrum are identified and explored, revealing infrared radiation beyond red, ultraviolet beyond violet, and still more energetic forms such as X-rays and gamma rays. The universe becomes filled with invisible light. Yet Maxwell's triumph also sets the stage for a deeper crisis. His theory treats electromagnetic radiation as a continuous wave whose energy can be spread smoothly through space. It explains propagation with extraordinary precision. It predicts interference, diffraction, polarization, reflection, refraction, and the existence of unseen wavelengths. But it does not explain every exchange between light and matter. Certain experiments will show energy arriving in indivisible amounts. A weak beam does not always deliver a faint continuous influence. It can produce isolated events. Electrons can be ejected from matter only when the light has sufficient frequency, regardless of how long low-frequency light shines. The wave is real, but the continuous classical picture is incomplete. Maxwell unites electricity, magnetism, and optics, removing one mystery while exposing another. Light is a wave in the electromagnetic field, yet it will soon behave as though the field can surrender its energy only in discrete packets. The invisible world becomes coherent, and then, at its foundations, begins to fracture again. Human vision occupies only a narrow opening in a much larger landscape of light. The colours from red to violet seem rich enough to contain an entire world, yet they represent only a small interval within the electromagnetic spectrum. Beyond red lie waves with longer wavelengths and lower frequencies. Beyond violet lie waves with shorter wavelengths and higher frequencies. None of these boundaries belongs to nature itself. They belong to the limits of the human eye. The electromagnetic field does not stop where sight stops. It continues smoothly through forms of radiation that remain invisible until instruments translate them into signals that can be measured. Once Maxwell's theory reveals that visible light is one part of a broader family, the universe changes character. Darkness no longer means absence. It may contain radio waves drifting between stars, infrared heat from cool dust, ultraviolet light from hot young suns, X-rays from violent collisions, and gamma rays from some of the most energetic events known. The invisible universe is not separate from the visible one. It is the same universe speaking through wavelengths that biology does not naturally detect. At the long wavelength end, radio waves stretch from lengths smaller than a person to distances greater than buildings, cities, and mountains. Their low frequencies make them well suited to carrying information over large distances. Oscillating electric currents in antennas produce them, and similar currents in receiving antennas respond when the waves arrive. Human technology uses this behavior for communication, navigation, broadcasting, and radar. But nature produces radio light as well. Electrons moving through magnetic fields emit radio waves. Clouds of hydrogen release characteristic radio signals. Pulsars send regular beams across space as rapidly rotating neutron stars sweep their radiation past distant observers. Radio telescopes therefore do not listen in the ordinary sense. They measure electromagnetic waves and convert them into electrical data. Their large dishes and networks reveal structures hidden behind dust, trace cold gas between stars, and map regions where visible light is weak or absent. Moving upward in frequency, microwaves occupy a shorter wavelength region. They heat food because certain materials absorb their energy efficiently, but the cosmic importance of microwaves is far greater. The oldest freely travelling light in the universe now arrives largely in this range. Expansion has stretched ancient radiation from the time when atoms first formed into the faint microwave glow that fills all space. Sensitive detectors measure tiny temperature differences across this background. Those differences preserve the seeds from which galaxies and clusters later grow. Microwaves also travel through clouds that block visible light, making them useful for studying cool material in the early universe. They show that a quiet-looking sky carries a nearly uniform afterglow from a time before stars exist. Infrared radiation lies closer to visible red. It is often associated with warmth because objects at familiar temperatures emit strongly in the infrared. A human body, a warm stone, a drifting cloud of dust, and the cool atmosphere of a planet all radiate invisible infrared light. This makes infrared astronomy especially valuable for studying regions too cold to shine brightly in visible wavelengths. Dust that appears as a dark obstruction in an optical telescope may glow in infrared. Within those clouds, stars are forming. Their visible light is absorbed and scattered, but longer infrared wavelengths escape more easily. Infrared instruments can therefore look into stellar nurseries, examine the heat of young planets, and detect distant galaxies whose visible and ultraviolet light has been stretched toward longer wavelengths by cosmic expansion. The same redshift that changes the ancient cosmic background also moves the light of very remote objects into the infrared, allowing modern telescopes to study earlier chapters of cosmic history. Visible light sits between infrared and ultraviolet, not because it holds a privileged position in physics, but because it passes relatively well through Earth's atmosphere and because the Sun emits strongly across this region. Life evolves under those conditions. Eyes become sensitive to wavelengths that are abundant and useful near the surface of the planet. The colours perceived by humans correspond to different responses in retinal cells. But the divisions between colours are constructed by biology. The electromagnetic spectrum itself is continuous. A wavelength does not carry a label saying blue or green. Colour emerges when radiation interacts with a visual system. Other creatures divide the spectrum differently. Some insects detect ultraviolet patterns on flowers. Certain snakes sense infrared radiation from warm prey. The world revealed to any organism is therefore only a selected portion of the physical light surrounding it. Beyond violet, ultraviolet radiation carries more energy per photon than visible light. The Sun emits it, and Earth's atmosphere absorbs much of the most harmful portion. Ultraviolet light can alter molecules, damage living tissue, and trigger chemical reactions. It can also reveal hot stars and energetic regions that appear less striking in visible wavelengths. Young massive stars shine strongly in ultraviolet, and their radiation can strip electrons from surrounding atoms. This process reshapes gas clouds and influences the birth of later stars. Ultraviolet observations also show activity around compact objects and the hot outer atmospheres of stars. Although invisible, this light leaves visible consequences in sunburn, fluorescence, and atmospheric chemistry. Fluorescent materials absorb higher energy photons and release part of that energy at longer visible wavelengths, turning unseen radiation into colour at still shorter wavelengths. X-rays carry enough energy to pass through soft tissue more easily than through dense bone, making them useful in medicine. In space, X-rays reveal environments far more extreme than ordinary stars. Gas heated to millions of degrees emits X-rays. Matter spiraling toward a neutron star or black hole can become hot enough to flood its surroundings with them. Supernova remnants, stellar coronae, colliding galaxy clusters, and powerful magnetic fields all produce X-ray radiation. Earth's atmosphere blocks most cosmic X-rays, protecting life but forcing X-ray observatories to operate above the atmosphere. Their detectors do not form images in the same way as ordinary cameras. X-rays are difficult to reflect directly because they tend to penetrate or be absorbed. Special mirrors guide them at shallow angles towards sensors. With these instruments, regions that look dark in visible light become bright with high-energy activity. Gamma rays extend beyond X-rays into the highest frequency region of the spectrum. Their photons carry enormous energy compared with visible light. Nuclear reactions can produce them, as can the decay of unstable particles and interactions involving matter and antimatter. In the universe, gamma rays emerge from radioactive elements, pulsars, black hole jets, supernova explosions, and brief events called gamma-ray bursts. Some of these bursts release extraordinary amounts of energy within a short time and arrive from galaxies billions of light-years away. Yet even here, the boundary between X-rays and gamma rays is partly historical and practical. The categories overlap. One method of classification emphasizes wavelength or photon energy. Another emphasizes origin, with gamma rays often associated with nuclear or particle processes and X-rays with electrons. Nature does not arrange the spectrum into perfectly separated boxes. The names are human tools placed across a continuous range. Across that range, the same basic laws apply. Radio waves reflect, refract, diffract, interfere, and polarize. Infrared waves do the same. X-rays and gamma rays also show wave behavior, though their short wavelengths require different scales and instruments to reveal it. All travel through vacuum at the same invariant speed. What changes is frequency, wavelength, and the energy carried by each photon. A radio photon has little energy. A gamma-ray photon has much more. Large numbers of low-energy photons can still carry substantial total energy, but individual interactions depend strongly on the energy of each quantum. This difference becomes crucial when light meets matter. Radio waves may gently drive electrons, infrared may excite molecular motion, visible and ultraviolet light may alter electronic states, X-rays can remove tightly bound electrons, gamma rays can penetrate deeply, break molecular bonds, or participate in particle reactions. The spectrum is therefore not merely a sequence of colours beyond sight. It is a sequence of different possible relationships between radiation and matter. Once instruments open these windows, every celestial object acquires multiple appearances. A galaxy in visible light shows stars and glowing gas. In radio, it may reveal cold hydrogen and jets from a central black hole. In infrared, dust and star formation emerge. In ultraviolet, hot young stars dominate. In X-rays, violent compact sources and heated gas appear. No single band gives the complete object. Reality arrives in layers, each selected by wavelength. The familiar sky is only one interpretation produced by human eyes. Beyond it lies an immense and active radiance, crossing space in forms that remain unseen until matter absorbs a photon and converts its energy into a trace. The universe is never truly dark. It is filled with light that vision alone cannot recognize. At the opening of the 20th century, light appears to be understood with extraordinary completeness. Maxwell's equations describe it as an electromagnetic wave. Interference, diffraction, polarization, reflection, and refraction all fit within that framework. Radio waves have been produced and detected. Invisible regions of the spectrum are steadily being mapped. The old particle theory seems to have been overcome. Yet a small set of experiments begins to reveal that the triumph is incomplete. The difficulty appears when light strikes matter and transfers energy to electrons. According to a classical wave picture, the energy of light is spread continuously across the wavefront. A brighter beam carries more energy because the electric and magnetic fields oscillate more strongly. A dimmer beam carries less. If the beam falls on a metal surface, its energy should accumulate gradually in the electrons there. Given enough time, even weak light should eventually provide enough energy to free an electron. The color of the light should matter less than the total energy delivered. But the metal does not behave this way. Under certain conditions, electrons leave the surface almost immediately. Their response depends strongly on the frequency of the light and not merely on its brightness. This phenomenon is called the photoelectric effect, and it exposes a gap between the smooth mathematics of classical waves and the abrupt events taking place inside matter. Experiments show a clear threshold. Light below a certain frequency fails to eject electrons from a particular metal, no matter how intense the beam becomes. Red light may shine brightly and still release nothing. Higher frequency light can produce electrons at once, even when the beam is faint. Increasing the brightness of that higher frequency light releases more electrons, but it does not give each electron unlimited energy. The energy of the emitted electrons is governed mainly by frequency. A more violet or ultraviolet beam produces faster electrons than a redder beam. Classical reasoning struggles with every part of this result. If energy is spread continuously, a strong low-frequency wave should eventually succeed. A weak high-frequency wave should require time to build up enough energy. Neither expectation matches the observations. The electrons behave as though light arrives in concentrated portions. One portion either contains enough energy to free an electron or it does not. The path toward this idea begins with another crisis, one involving the glow of hot matter. Every object with a temperature emits electromagnetic radiation. A warm surface radiates mainly in the infrared, while a hotter object begins to glow red, then orange, then white, as the distribution shifts towards shorter wavelengths. Classical physics attempts to calculate this spectrum by treating the electromagnetic field inside a cavity as a collection of standing waves. The theory predicts that higher and higher frequencies should contain ever more energy. Taken literally, the total becomes unbounded, implying that hot objects should pour out enormous amounts of ultraviolet radiation. Real objects do nothing of the kind. The prediction fails so badly that it later becomes known as the ultraviolet catastrophe. Max Planck finds a mathematical escape. He assumes that the oscillators exchanging energy with radiation cannot gain or lose arbitrary amounts. Their energy changes in discrete steps. The size of each step depends on frequency through a new constant of nature, now called Planck's constant. Planck initially treats this quantization cautiously, more as a formal rule than as a complete description of reality. The electromagnetic field itself can still be imagined as continuous. Matter merely exchanges energy with it in restricted amounts. The formula works, but its meaning remains unsettled. Albert Einstein takes the next step. In 1905, he argues that the discreteness cannot belong only to the material emitters and absorbers. Light itself must sometimes behave as though its energy is concentrated into localized packets. Each packet carries an amount proportional to the frequency. Higher frequency light comes in more energetic packets. Lower frequency light comes in less energetic packets. Brightness does not change the energy of an individual packet. It changes how many packets arrive. This simple distinction reorganizes the photoelectric effect. An electron in a metal is bound by an energy barrier. To escape, it must receive at least a minimum amount in a single interaction. A low-frequency packet carries too little, so no electron is released, even if many such packets arrive. Their energies are not normally pooled into one electron in the required way. A high-frequency packet carries enough energy to overcome the barrier. Any energy left after escape becomes motion, so the electron departs faster when the incoming frequency is higher. A brighter high-frequency beam contains more packets, and therefore frees more electrons, but each event remains governed by the energy of one packet. The abrupt response is no longer mysterious. The electron does not slowly drink from a continuous wave. It receives a discrete transfer. This packet is later called a photon. The name does not mean that light has returned to Newton's tiny hard corpuscles. A photon is not a miniature glowing grain with a hidden surface and a definite classical path. It is a quantum of the electromagnetic field, an indivisible amount of excitation exchanged in an interaction. Its energy is tied to frequency, and its momentum is tied to wavelength. These relations connect the wave description directly to the particle-like event. Frequency and wavelength belong naturally to waves, while discrete energy and momentum resemble particles. The photon joins these properties without fitting completely into either classical picture. At first, Einstein's proposal meets resistance. Maxwell's wave theory is too successful to discard. An interference seems to require radiation spread across space. Even Planck hesitates to accept light quanta as fully real. The idea appears to threaten the continuity of the electromagnetic field, yet evidence accumulates. Measurements of the photoelectric effect confirm the predicted relation between electron energy and light frequency. The threshold behavior remains exact. The delay expected from gradual energy accumulation does not appear. Light exchanges energy in events that are countable and localized. A second powerful confirmation comes from the scattering of high-energy radiation by electrons. Arthur Compton directs X-rays at matter and studies how the outgoing radiation changes. The scattered X-rays emerge with longer wavelengths, while electrons recoil. The result can be calculated by treating the interaction as a collision between two objects carrying energy and momentum. The incoming photon gives part of both to the electron, and departs with reduced energy and increased wavelength. A purely continuous classical wave treatment cannot reproduce the observed relation as naturally. The photon behaves in the collision like a particle. Despite having no rest mass, it carries momentum and can push. Radiation pressure, already present in Maxwell's theory, gains a quantum interpretation. A beam exerts force because photons transfer momentum when absorbed or reflected. On ordinary scales, each transfer is tiny, but vast numbers of photons create a measurable pressure. This pressure acts on dust near stars, shapes comet tails, and can propel reflective sails through space. The quantum picture does not erase the classical one. A bright beam containing an enormous number of photons behaves with such smooth regularity that Maxwell's continuous fields provide an excellent approximation. Radio antennas, lenses, mirrors, and many optical systems can be designed without tracking individual photons. Classical electromagnetism remains true within its domain, just as the smooth surface of water remains useful even though water is made of molecules. Quantum theory becomes necessary when individual exchanges matter, when light is faint, when frequencies are high, or when detectors are sensitive enough to register single events. The wave has not vanished. Interference and diffraction remain. What changes is the belief that energy can always be divided without limit. Light may spread according to a wave-like structure, yet it is emitted and absorbed in discrete acts. This creates a deeper question than the old choice between waves and particles. A photon is born when a quantum system loses energy and is destroyed when another gains it. Between those events, the theory assigns probabilities, phases, and possible paths. At the point of detection, the energy arrives whole. There is no fraction of the same photon deposited at several distant detectors. The event is singular, even when the pattern formed by many events is wave-like. Einstein's explanation therefore solves the photoelectric effect by opening a more unsettling view of nature. Reality at small scales does not merely hide details behind limited instruments. It organizes physical change into quanta. The continuous brightness of the world is built from countless indivisible exchanges, each one linking the rhythm of a wave to the sudden arrival of a particle-like event. The word photon suggests a tiny object, something compact enough to be imagined crossing space like a grain of dust or a microscopic bead. That image is useful only for a moment. A photon is not a small piece of ordinary matter. It has no rest mass, no solid surface, and no hidden internal engine carrying it forward. It is a quantum of the electromagnetic field, a discrete amount of excitation that can be emitted, travel, and later be absorbed. Its energy is not arbitrary. It is linked directly to frequency. Higher frequency light carries more energy in each photon, while lower frequency light carries less. A gamma-ray photon therefore carries far more energy than a radio photon. Even though both move through vacuum at the same speed, the speed does not distinguish them. Their frequency and wavelength do. This already separates photons from familiar particles. A stone can move slowly or quickly while remaining the same stone. A photon in vacuum cannot be slowed into a resting state. If its frequency changes, its energy changes, but it still moves at the universal speed of light. The absence of rest mass is fundamental. It defines the kind of path a photon can follow through space-time. Objects with mass can remain at rest in some frame, and can be accelerated through a range of speeds below light. A photon has no such rest frame. There is no valid viewpoint in which it sits still while the universe moves around it. Its existence is tied to motion at the speed of light. Yet masslessness does not mean powerlessness. A photon carries energy, and energy contributes to physical change. It also carries momentum, the quantity associated with motion, and the ability to transfer a push. For ordinary massive objects, momentum is often pictured as mass multiplied by velocity. That familiar expression does not apply directly to light, because the photon has no rest mass. Relativity provides a broader relation in which energy and momentum remain linked, even when rest mass is zero. For a photon, momentum is proportional to energy, and inversely related to wavelength. Shorter wavelength photons carry more momentum than longer wavelength photons. When a photon is absorbed, reflected, or scattered, that momentum must be transferred or redirected. The receiving matter recoils. Even if the effect of a single event is extremely small, this is how light pushes. The pressure of sunlight is weak on human scales, but it is real and persistent. A surface that absorbs light receives the forward momentum of the incoming photons. A reflective surface can receive a larger change because the photons reverse direction, producing a greater transfer of momentum. Over time, this force can influence dust grains, alter the motion of small objects, and drive a solar sail. In the tail of a comet, radiation pressure helps push fine dust away from the sun, around luminous stars. It can affect surrounding material and compete with gravity. Light remains weightless in the sense of having no rest mass, yet it participates in exchanges of energy and momentum. The creation of a photon is equally unlike the manufacture of an ordinary object. In many cases, a quantum system begins in a higher energy state and changes to a lower one. The missing energy appears as a photon. An atom offers the clearest example. Its electrons do not orbit the nucleus along little planetary tracks. They occupy quantum states, patterns allowed by the structure of the atom. Each state has a definite energy. When the atom changes from a higher state to a lower state, it can emit a photon whose energy equals the difference between them. The photon does not sit inside the atom beforehand as a stored particle waiting to escape. It comes into existence through the transition. Its frequency reflects the size of the energy gap, because each element has its own set of allowed states. The photons it emits form characteristic spectral lines. Hydrogen produces one pattern, helium another, iron another. These lines allow distant matter to be identified from light alone. A star sends out photons created in countless transitions, and their energies preserve information about the atoms that release them. Emission is not limited to atoms. Molecules emit photons when their rotational or vibrational states change. Atomic nuclei emit gamma rays when they move between nuclear energy levels. Charged particles emit radiation when their motion changes. Matter and the electromagnetic field exchange energy through many processes, but the quantum appears as a whole. A photon may be very low in energy or extremely energetic, yet it is not normally divided during a simple absorption event. When a detector captures one photon, the entire quantum is transferred into the receiving system. The photon ceases to exist as an independent excitation, and its energy becomes another form. It may raise an electron to a higher state, break a molecular bond, generate electrical current, warm a material, or trigger a chain of reactions. Absorption is not the photon coming to rest inside matter. There is no stationary photon hidden in the detector. The field excitation is removed, and the receiving system changes. This gives the photon a peculiar life history. It begins in an interaction and ends in another. Between those endpoints, quantum theory does not require it to resemble a tiny classical projectile following a perfectly defined route. Its state can spread, interfere, and involve multiple possible paths. Yet detection occurs at a localized place and time. A camera sensor may register a single spot. A photomultiplier may produce a pulse. A retinal molecule may change shape. The result is discrete. Many such events gradually build the smooth image of a star, a face, or a landscape. Apparent continuity emerges from enormous numbers of individual exchanges. Even a dim light still consists of photons, though they may arrive sparsely enough to be counted one by one. The brightness of a beam depends partly on how many photons pass through a region during a given interval. Its color depends on the distribution of their frequencies. A bright red beam can carry more total energy than a faint blue beam, because it contains many more photons, even though each blue photon carries more energy than each red one. This distinction is essential. Total energy belongs to the whole beam. Quantum energy belongs to each photon. The same principle explains why intense low-frequency light cannot always cause a high-energy transition. An individual photon must carry enough energy to match the process. Increasing intensity adds more low-energy photons, not more energy to each one. Photons also carry angular momentum. Part of this appears as polarization, a property linked to the orientation and handedness of the electromagnetic field, in quantum language. A photon has an intrinsic form of angular momentum called spin. This does not mean that a photon is a tiny sphere rotating in space. The word spin names a quantum property that behaves mathematically like angular momentum, but has no exact classical picture. Circularly polarized light carries angular momentum that can be transferred to matter, producing tiny torques. Photons can therefore push and twist, despite lacking rest mass and ordinary material structure. Their properties are defined not by resemblance to familiar objects, but by the symmetries and rules of the field they belong to. The photon's lack of electric charge is another important feature. It does not respond directly to electric and magnetic fields in the way an electron does. Ordinary light beams pass through one another without scattering, because photons do not usually interact strongly with other photons. Their effects become visible through interactions with charged matter, in extreme conditions. Quantum processes can allow light to influence light indirectly through temporary particle interactions, but such events are rare at ordinary energies. Most photons cross space independently, carrying information without disturbing one another. This allows countless signals to overlap in the same region. Starlight, radio broadcasts, thermal radiation, and the cosmic microwave background can pass through the same room or the same volume of space, each retaining its own structure until matter absorbs it. The photon is therefore neither a miniature object nor a mere bookkeeping device. It is the smallest transferable unit of electromagnetic excitation, possessing energy, momentum, polarization, and quantum identity without rest mass. It can be created and destroyed, but not gradually worn away like matter. It can cross the universe without aging in an ordinary sense, yet it can end in a single microscopic event. It follows rules that preserve energy and momentum exactly while refusing the comforting picture of a permanent little body. In the photon, wave and particle language begin to merge. Frequency determines energy. Wavelength determines momentum. A spreading quantum state produces localized impacts. The object at the center of light is not a compromise between two classical ideas. It is a different kind of reality, one in which what travels and what arrives cannot be described by the same simple image. A beam of light becomes faint enough that its photons arrive one at a time. Ahead stands a barrier with two narrow openings, and beyond it waits a detector capable of recording each arrival as a tiny localized mark. If a photon is only a particle, the description appears straightforward. It passes through the left slit or the right slit and strikes the screen at one point. If it is only a classical wave, the wave passes through both openings, spreads, overlaps, and forms an interference pattern. The experiment combines both expectations and then refuses to obey either one completely. Each photon arrives as a single event. No detector sees half a photon at one place and the other half elsewhere. Yet after many photons pass through the apparatus, one by one, their separate marks gradually assemble into the same bright and dark bands produced by an ordinary wave. The pattern appears even when the delay between photons is long enough to ensure that only one quantum is present in the apparatus at a time. There is no second photon nearby with which the first can interfere. The quantum behaves as though its own alternatives overlap. This result reaches beyond the old argument about whether light consists of waves or particles. It shows that both classical pictures fail when treated as literal descriptions. The photon does not behave like a tiny ball secretly choosing one slit, while an ordinary physical wave travels beside it. Nor does it behave like a continuous splash of energy divided across the screen. Its state develops according to wave-like rules, while its detection remains indivisible and localized. The interference pattern belongs to probability rather than to a material fluid. Quantum theory assigns an amplitude to each possible outcome. An amplitude is not an ordinary probability. It carries both size and phase, allowing alternatives to reinforce or cancel before probabilities are calculated. For the two slits, one amplitude is associated with reaching a point on the detector through the first opening, and another with reaching the same point through the second. The amplitudes combine. Where they reinforce, detection becomes more likely. Where they cancel, detection becomes unlikely or effectively impossible. The dark bands do not mean that photons arrive there and erase one another after impact. They mean the combined amplitude for arriving there vanishes before any event occurs. This structure explains why the final pattern is wave-like, even though every registered photon is particle-like. The quantum state spreads across possible routes. The event selects one location. The experiment becomes stranger when an attempt is made to determine which slit the photon uses. A detector placed at the openings can record passage through one side or the other, once reliable path information exists. The interference pattern disappears. The screen then shows a distribution closer to the sum of two single-slit patterns. It is tempting to say that human knowledge changes reality, but that wording is too vague. No conscious observer is required. The decisive change comes from a physical interaction that connects the photon's path with another system. The path becomes recorded in principle. Information about the alternatives is deposited in the apparatus or environment, and the two possibilities can no longer combine with the same coherent phase relationship. Measurement in quantum mechanics is therefore not merely looking, it is an interaction that creates distinguishable records. A photon entangled with a path detector is no longer described independently of that detector. The total state contains correlations. One part associates the photon with the left path and one detector record, while another associates it with the right path and a different record. Because those records are distinguishable, interference between the alternatives becomes unavailable in the ordinary screen pattern. This process is closely related to decoherence, the loss of observable phase relationships, when a quantum system becomes entangled with many uncontrolled degrees of freedom. Decoherence helps explain why large objects do not normally display obvious interference. A dust grain, a measuring device, or a person interacts constantly with surrounding light, air, heat, and matter. Information about its location spreads rapidly into the environment. The delicate phase relationships required for visible superpositions become inaccessible. The underlying quantum rules remain, but classical behavior emerges as interference between macroscopically distinct alternatives is suppressed. For an isolated photon, coherence can survive across large distances. The two paths need not be equally simple. Mirrors and beam splitters can guide them through an interferometer, separating and recombining the alternatives. A beam splitter is a partly reflective surface that gives a photon more than one possible route. When the paths reunite, their amplitudes interfere. A small change in path length alters the phase and shifts the detection probabilities. Instruments based on this principle can measure extraordinarily tiny changes in distance. The same quantum behavior that challenges ordinary language becomes a tool of extreme precision. Yet the apparatus does not reveal a hidden classical story beneath the mathematics. Asking which route the photon truly follows when no path record exists assumes that one definite route must be present. Quantum theory does not generally supply that fact. It supplies the state, the possible outcomes, and the probabilities produced by their amplitudes. Different interpretations add different pictures of what may underlie this structure, but experiments agree on the observed pattern. Richard Feynman expresses quantum propagation through a method that considers all possible paths between emission and detection. This does not mean that a photon literally divides into countless miniature copies, each travelling along a visible road. It means that the calculation assigns a phase contribution to every allowed path. Paths close to the classical route tend to reinforce one another, while wildly different paths often cancel through rapidly changing phases. On large scales, the surviving combination makes light appear to follow the familiar path of least travel time. Reflection and refraction emerge from the sum over alternatives. The straight ray of geometric optics is therefore not necessarily a primitive track. It is the large-scale result of quantum amplitudes combining across many possibilities. In the double-slit experiment, The geometry preserves two broad families of paths, and their phases generate fringes. Blocking one slit removes one family and changes the pattern. Adding a device that marks the route changes the correlations and destroys the interference. Every alteration to the available alternatives changes what can combine. The phrase wave-particle duality remains useful, but it can also mislead. It suggests that light switches between two complete identities, appearing as a wave on some days and a particle on others. Quantum light is not secretly one classical object wearing two masks. Wave and particle are partial analogies drawn from the large-scale world. The wave analogy captures interference, phase, diffraction, and spread. The particle analogy captures discrete detection, indivisible energy transfer, and localized momentum exchange. The photon itself belongs to quantum theory, where states can be superposed and outcomes occur probabilistically. Its properties are not contradictions once the demand for a classical picture is released. The contradiction arises only when mutually incomplete analogies are forced to describe the whole process. This distinction becomes especially clear in delayed choice arrangements. A measurement setup can be changed after the photon has entered an interferometer, determining whether the final apparatus reveals interference or path information. The results do not require the photon to receive a message backward in time and revise a completed history. Instead, they show that classical history was never established in the first place. The experiment defines what kinds of correlations can appear at the end. A wave-like pattern and definite path information are complementary. The apparatus can be arranged to reveal one or the other, but not both with unlimited precision in the same event. Quantum eraser experiments deepen the lesson by showing that interference can be recovered in carefully selected correlations when path information is rendered indistinguishable. Nothing physical is erased from the past. The relevant alternatives become capable of interfering within a particular subset of the data. These experiments are often described in dramatic language, yet their real meaning is quieter and more profound. Quantum events cannot always be assigned the independent, observer-free histories expected from classical objects. The available information, the physical arrangement, and the correlations between systems form part of the phenomenon. The photon remains real, but its reality is not the reality of a tiny bead following a concealed line. It is represented by a quantum state that carries structured possibilities from one interaction to the next. At emission, energy and momentum leave matter in a discrete amount. During propagation, amplitudes spread and interfere. At detection, another discrete exchange occurs. Between those endpoints, no single classical image remains faithful to the evidence. Light behaves as both wave and particle only because nature is neither. The deeper description allows alternatives to coexist, combine, and cancel. While each actual encounter leaves one definite mark, one event appears on the screen, but the probability of that event carries the influence of every path that remains possible. The photon becomes less like an object the closer physics looks at its foundations. A detector records a localized event, and an experiment may count one photon at a time. Yet the underlying theory does not begin with tiny particles moving through a pre-existing emptiness. It begins with fields. In classical physics, a field assigns a value to every point in space and time. A gravitational field assigns an influence to every region around matter. Maxwell's electromagnetic field assigns electric and magnetic values throughout space, allowing light to travel as a self-propagating wave. Quantum field theory keeps the idea of a field but changes its meaning. The field becomes a quantum system with allowed states, uncertainties, fluctuations, and discrete excitations. A photon is one such excitation of the electromagnetic field. It is not best pictured as a bead placed inside the field. It is a state of the field itself. A ripple on water is not a separate substance added to the pond. It is the pond arranged in a moving pattern. The comparison is incomplete, yet it points in the right direction. The photon does not travel through the electromagnetic field as a boat travels through water. The photon is the field in an excited quantum state. When the excitation is absorbed, the field returns to a lower energy state while matter gains the transferred energy and momentum. Nothing material needs to survive as a permanent little traveller between those events. The field persists. Individual photons can appear and disappear. This reverses the usual hierarchy of things. In everyday thought, objects seem fundamental, and fields seem like effects surrounding them. Quantum field theory suggests the opposite. The fields are fundamental, while particles are temporary manifestations of those fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks arise from quark fields. Other known particles correspond to other fields. Empty space is therefore not a container waiting to be filled. It is the lowest energy state of many quantum fields, a state called the vacuum. The vacuum has no ordinary particles, but it is not absolute nothingness. The fields remain present, and their quantum structure does not vanish. Space is not simply crowded with classical particles flickering like sparks. Vacuum fluctuations are properties of quantum states and correlations, not necessarily tiny objects enjoying brief hidden lives. The field description becomes necessary because special relativity allows energy to create and destroy particles. In ordinary quantum mechanics, a fixed number of particles may be described by a wave function, but high enough energy can produce new particles, while particles and antiparticles can annihilate into radiation. A theory built on an unchanging collection of objects cannot handle such processes naturally. A quantum field can. Its excitations are countable, but their number need not remain fixed. One atom can emit a photon. 2 photons can emerge from a decay. A photon with sufficient energy can contribute to the creation of a particle and its antiparticle when conservation laws and surrounding conditions permit. Matter can become light, and light can become matter, not because one substance is magically transformed into another, but because energy moves among coupled quantum fields. The electromagnetic field couples most directly to electrically charged fields. An electron carries charge, so the electron field interacts with the photon field. In an atom, the combined quantum system has possible energy states. When the atomic state changes, the electromagnetic field may gain 1 quantum of excitation. The result is a photon. At absorption, the process reverses. The field loses 1 quantum while the atom or detector changes state. Emission and absorption are allowed transitions within one coupled system. The same framework explains scattering. An incoming photon interacts with a charged particle, and an outgoing photon and change particle state emerge. Feynman diagrams provide a compact visual language for organizing the possible interactions. Lines represent matter fields, while wavy lines represent the electromagnetic field. At a vertex, the fields couple. Yet the diagram is not a literal picture of tiny particles meeting at a sharply defined crossroads. It is a bookkeeping device for terms in a probability calculation. Internal lines are especially easy to misunderstand. They're often called virtual particles, but they are not ordinary detectable photons traveling secretly between charges. They represent intermediate mathematical contributions within an interaction. The familiar electric force between charged objects emerges from this deeper quantum description. 2 electrons repel. In classical physics, each produces an electric field, and each responds to the field of the other. In quantum electrodynamics, the interaction is calculated through the coupling of the electron and photon fields. At ordinary distances and energies, The quantum result reproduces the smooth classical force with extraordinary accuracy. The classical field is not discarded as false. It appears as a large-scale approximation to the quantum field when enormous numbers of quanta and interactions combine. A radio wave may contain so many photons that describing each one separately is unnecessary. The electromagnetic field then behaves almost like Maxwell's continuous wave. A coherent state of the quantum field can closely resemble a classical oscillation. Lasers produce light with a high degree of coherence, meaning the field maintains a stable phase relationship. Even there, detection occurs in quantum events. The classical wave and the photon description are not competing substances. They are different levels of description applied to the same field. This becomes clearer when considering what a single photon looks like in space. A photon does not need to occupy one mathematical point. Its quantum state can be spread across a broad region. A carefully prepared photon may have a narrow range of frequencies and therefore a long spatial extent. Another may be localized more tightly but contain a broader spread of frequencies. This reflects a general quantum relationship between localization and momentum. The photon state can also involve several directions, paths, or polarization components at once. When a detector absorbs it, the outcome is localized, but the field state before absorption may not have assigned it one classical position. The particle-like mark is a feature of the interaction, not proof that a tiny sphere has followed a hidden trajectory. Even the idea of photon number has limits. In some quantum states, the number of photons is definite. In others, it is uncertain. A classical-looking electromagnetic wave can correspond to a state that contains a range of possible photon numbers. This is not ignorance about a fixed hidden total. The quantum state itself does not assign one exact number before measurement. Likewise, the vacuum is not simply the state with all field properties exactly zero. Certain quantities fluctuate within limits set by quantum uncertainty. Quantum electrodynamics, the quantum field theory of light and electrically charged matter, becomes one of the most precisely tested frameworks in science. It predicts subtle shifts in atomic energy, the magnetic behavior of electrons, and the detailed probabilities of scattering processes. Agreement between theory and experiment reaches remarkable precision. This success does not provide a simple picture of what reality looks like beneath the equations. Instead, it shows that the field framework captures relationships and outcomes with exceptional reliability. The desire for a familiar image remains unsatisfied. A field is imagined as something spread through space, while a particle is imagined as something located. The photon belongs fully to neither picture because the quantum field can be spread and still exchange energy discretely. It can interfere like a wave and produce a single click like a particle. The apparent contradiction fades once the field is treated as primary. Wave behavior describes how the quantum state evolves. Particle behavior describes how energy and momentum are exchanged. Both emerge from one underlying structure. Light, therefore, does not alternate between being a wave and being a particle. It remains an excitation of the electromagnetic field throughout the process, while different experiments reveal different features of that excitation. This answer is deeper than the old categories, but it is also less visual. The photon dissolves as a miniature object and reappears as a pattern of possibility in a field that extends across space. Reality becomes less like a collection of things and more like a network of fields capable of changing state, coupling, and exchanging quanta. The visible world, from starlight to the colors of a leaf, is built from these exchanges. Every image begins when the electromagnetic field changes somewhere, evolves through space, and changes matter elsewhere. What appears as a ray-crossing emptiness is, at the deepest tested level, the motion of no separate substance at all. It is the field itself carrying a quantum difference from one interaction to the next. Measurement changes the character of a quantum question. Before detection, a photon may be described by a state spread across several paths, frequencies, polarizations, or possible destinations. After detection, one definite event appears. A detector clicks at one place. An atom changes energy. A molecule in the retina shifts shape. The transition from many structured possibilities to one recorded outcome is among the deepest puzzles in physics. Quantum theory predicts the probabilities of those outcomes with extraordinary success, yet it does not supply a single universally accepted account of how one result becomes actual. The mathematics describes a state that evolves smoothly until an interaction produces a record. At that point, the description seems to change. The possibilities no longer interfere in the same way. One outcome is found, and the others are absent from that observation. This is often called the measurement problem, though the word measurement can mislead. No laboratory technician or conscious mind is required. A measurement is any physical process that creates a stable correlation between a quantum system and something else. A photon strikes a detector, and the detector changes. That change may be amplified into a current, a flash, a stored bit, or a chemical reaction. The important feature is that information about the outcome becomes embedded in the world. The detector has not merely watched the photon from a distance, it has interacted with it and become part of the combined quantum system. Before the interaction, the photon may occupy a superposition of alternatives. Afterward, the photon and detector are entangled. Entanglement means that the full state cannot be divided into independent descriptions of each part. One possible branch contains a photon associated with one detector response. Another contains a different possibility associated with another response. The parts are correlated so deeply that describing one alone loses information contained in the whole. This structure has no exact classical equivalent. Two gloves placed in separate boxes are correlated because one is left-handed and the other right-handed, but each glove already possesses its property before the boxes are opened. Quantum entanglement is stronger. In many experiments, the theory does not assign each particle a complete set of independent local properties waiting to be revealed. The correlations exist, yet the individual outcomes are not fixed in the classical way. Photons provide some of the clearest demonstrations. A source can produce two photons in an entangled polarization state. The pair is arranged so that measurements performed along matching orientations show coordinated results. If one photon is detected far away, the outcome is correlated with what can be found for the other. The correlation can persist across great distance. Yet this does not allow a usable message to travel faster than light. Each local result remains unpredictable. Only when records are later compared does the pattern become visible. Entanglement therefore challenges the idea that distant objects always possess fully separate realities. But it does not overturn relativity by creating a controllable superluminal signal. The tension becomes sharper through tests inspired by John Bell. Bell shows that certain quantum predictions cannot be reproduced by any theory in which particles carry only local hidden instructions that determine every outcome in advance. Experiments with entangled photons repeatedly violate the limits that such local hidden variable theories must obey. The results support quantum mechanics and rule out a broad class of classical explanations. Nature preserves correlations that cannot be understood as ordinary shared plans carried from the source. Something about the combined quantum state is more fundamental than separate local descriptions. This does not force one single philosophical interpretation, but it narrows the possibilities. Reality cannot be both fully local and classically predetermined in the simple way familiar from everyday objects. Measurement also brings uncertainty into focus. Quantum uncertainty is not merely the result of clumsy instruments. Certain pairs of properties cannot simultaneously possess arbitrarily sharp values within the same state. Position and momentum form one such pair. Different components of polarization and angular momentum show related limits. Preparing a photon with a very precise frequency requires a state extended over a long duration, while localizing it tightly in time requires a broader spread of frequencies. These are not defects in equipment. They arise from the mathematical structure of waves and quantum states. A sharply defined property in one description demands a spread in its complementary partner. This prevents the photon from carrying every classical attribute at once. The question of what it is doing between interactions therefore becomes dangerous. Classical language assumes a complete history, a position at every moment, a route through every region, and a set of properties that exist whether or not anything probes them. Quantum theory often does not assign such a history. It provides amplitudes for possible outcomes and rules for how those amplitudes evolve. When an experiment is arranged to reveal interference, the alternatives remain coherent and no definite path is recorded. When it is arranged to reveal path information, interference disappears. The two arrangements do not uncover different hidden layers of the same classical journey. They define different physical questions, and quantum theory gives answers suited to each. This is sometimes described through complementarity. Features such as path and interference are not simultaneously available with unlimited clarity, because the conditions required to reveal one disturb or exclude the conditions required to reveal the other. The photon is not hiding a full classical story behind the apparatus. The experimental context helps determine which properties can become definite and recordable. Different interpretations explain this in different ways. In one family of views, often associated with the Copenhagen tradition, the quantum state is a tool for predicting outcomes, and measurement marks the point where classical records appear. Questions about an unmeasured path may be treated as lacking a physical answer rather than possessing a hidden one. In many worlds approaches, the quantum state never collapses. All branches continue within a larger state, while observers become correlated with particular outcomes and experience only their branch. In objective collapse models, the smooth quantum evolution is modified so that superpositions genuinely reduce under certain conditions. In pilot wave theories, particles possess definite positions guided by a non-local wave. Relational and information-centered interpretations offer still other accounts, treating properties as meaningful only relative to interactions or emphasizing the structure of possible information. These views differ profoundly in ontology, yet most reproduce the same tested predictions in ordinary experiments. The disagreement survives because the mathematics works better than the available pictures. Decoherence explains part of the transition without fully settling it. A quantum system rarely remains isolated. It interacts with air, heat, stray radiation, and countless surrounding degrees of freedom. These interactions entangle the system with the environment. The phase relationships between large-scale alternatives spread into correlations too complex to track. Interference then becomes effectively impossible to observe, and the system appears classical. A detector pointer does not remain visibly suspended between positions because the environment records its state almost instantly in scattered photons, vibrating molecules, and thermal motion. Decoherence explains why certain stable outcomes dominate and why the classical world emerges from quantum rules, yet it does not by itself explain why one particular outcome is experienced rather than another. It transforms a clean superposition into a set of non-interfering branches. But the question of uniqueness remains interpretation dependent. Light sits at the center of these issues because photons are both messengers and agents of measurement. A photon scattered from an object can carry away information about position. That information may destroy interference for the object, even if no one ever captures the photon. The environment is constantly measuring in this broad physical sense. Sunlight, thermal radiation, and background photons continually entangle with matter, making large objects appear definite. The visible world is therefore classical, partly because light is always touching it and carrying records away. Yet the same photons, when isolated with care, reveal superposition, entanglement, and interference. Light helps create the stable reality of everyday experience, while also exposing the uncertainty beneath it. At the point of contact, a possibility becomes a record. Before contact, the photon is described by a quantum state that may resist every attempt to assign a single classical history. After contact, an event belongs to the world of facts. The border between those descriptions is not a wall in space, it is a change in relationship, where an isolated possibility becomes entangled, amplified, and preserved. Quantum theory predicts the pattern of these events with unmatched precision, but the meaning of the transition remains open. Reality appears sharp where interactions leave records, while between them it is governed by amplitudes, correlations, and alternatives that cannot be pictured as ordinary things. The photon therefore does more than illuminate objects. It reveals that definiteness itself may be an achievement of interaction, emerging only when the quantum world leaves a trace that cannot be undone. Light crosses the universe at the one speed that every observer in empty space must measure to be the same. This is not a convenient property added to an otherwise ordinary theory. It is the central fact that forces space and time to change their meaning. In the older Newtonian picture, distances and durations belong to a single universal stage. Clocks may run badly and rulers may bend, but space itself remains fixed, and time passes at the same rate everywhere. Light seems to move through that stage as any fast object would, only much faster. Special relativity replaces this picture. The speed of light is not measured relative to an invisible ether, nor relative to the source that emits it. An observer moving toward a beam and an observer moving away from it still measure the same speed in vacuum. Their measurements of distance, duration, and simultaneity adjust instead. Space and time are no longer separate absolutes. They form a single geometry called space-time, and light traces the boundary that divides what can be causally connected from what cannot. A flash emitted from one event spreads outward, defining the fastest route by which information or influence can reach another place. Nothing carrying ordinary matter can overtake it. Massive objects move within the structure set by light, while light itself follows paths that mark the structure's edge. This is why the history of a photon cannot be described in the same way as the history of a planet, an atom, or a clock. A massive object follows a time-like path through space-time. Along that path, it can carry a clock, and the clock records proper time, the time experienced by an observer moving with the object. Two clocks that separate, travel differently, and reunite may record different durations because their paths through space-time differ. This is not an illusion or a failure of the instruments. It is a property of space-time confirmed by fast particles, precise clocks, and technologies that must correct for relativistic effects. Light follows a null path, also called a light-like path. Along such a path, the space-time interval between emission and absorption is zero. In this precise geometrical sense, no proper time accumulates between the two events. Yet the phrase from the photon's point of view remains dangerous. A photon has no valid rest frame. No physical observer can accelerate to the speed of light, match the photon, and place a clock beside it. The transformations used by relativity become singular at that limit for a massless object. It is therefore better to say that light connects events along a path of zero proper time than to claim that a photon literally watches the universe freeze. The mathematics is clear even when ordinary language becomes strained. From the perspective of observers made of matter, light may travel for billions of years and cross billions of light years. A photon released in the early universe may arrive in a detector after galaxies form, stars burn, planets assemble, and life emerges. The emission and absorption are widely separated in cosmic history, yet the geometric interval along the photon's route remains null. Distance persists for the observers who measure it. Cosmic time passes for the universe through which the light moves. Proper time along the light-like path does not. These statements are not contradictions because they refer to different measures within space-time. The strangeness comes from expecting one universal time to govern everything. Relativity removes that expectation. Light also reveals that space-time is not always flat. General relativity describes gravity not as a force pulling across a rigid background, but as curvature produced by mass and energy. Matter influences the geometry, and the geometry influences motion. A planet follows the straightest available path through curved space-time. Light does the same. Because the geometry is curved, that straightest path may appear bent when mapped against ordinary space. A ray passing near a star changes direction. Light from a distant galaxy may curve around a cluster and reach Earth along several routes. The foreground mass behaves as a gravitational lens, producing arcs, rings, magnified images, or multiple copies of the same source. The bending is not evidence that photons secretly possess rest mass. Their energy and momentum respond to space-time geometry, and their null paths follow that geometry exactly. Gravitational lensing turns light into a map of invisible structure. The amount and pattern of bending reveal the distribution of matter, including matter that emits little or no light of its own. Galaxies and clusters distort the images behind them. Small distortions measured across many distant galaxies allow astronomers to infer large webs of mass. Light therefore carries information not only about the object that emits it, but also about every gravitational landscape through which it passes. Its path becomes a record of curved space-time. Gravity also changes frequency. Light climbing away from a massive body is measured at a lower frequency by distant observers. Its wavelength becomes longer, an effect called gravitational redshift. Light falling deeper into a gravitational field is measured at a higher frequency. The photon is not losing energy through friction. Energy in general relativity depends on the observer and the geometry used to compare measurements at different locations. The shift reflects how clocks run at different rates in curved space-time. Near stronger gravity, clocks tick more slowly relative to clocks farther away. Since frequency is the rate at which wave cycles arrive, altered clock rates change the measured colour and energy of light. The spectrum carries the imprint of gravity. Cosmic expansion produces another kind of redshift as light crosses an expanding universe. The wavelength associated with it grows with the scale of space. A photon emitted as visible or ultraviolet light from an early galaxy may arrive billions of years later in the infrared. Ancient radiation from the era when atoms first form has been stretched into microwaves. This is not well described as light simply becoming tired. It is a consequence of propagation through a changing space-time. The distance between large, unbound regions grows while the photon travels, and the wave's wavelength grows with it. The observed frequency falls, and so does the photon energy measured by later cosmic observers. In a universe without a single global conservation law for energy across changing space-time, asking where that lost energy goes may not have one simple answer. Local interactions still conserve energy and momentum, but comparing the energy of light across the evolving cosmos requires care. Redshift turns light into a clock of expansion. Spectral lines known from laboratories appear displaced toward longer wavelengths in distant galaxies. The greater the expansion accumulated during the journey, the greater the shift tends to be. From this evidence, the history of cosmic growth can be reconstructed. Yet the same observations also contain motion, gravity, and local environmental effects. So, interpretation depends on separating several causes. Light does not arrive carrying labels for each influence. Its spectrum must be read as a layered record. The photon's journey is therefore both simple and profound. It leaves one interaction, follows a null route through space-time, and ends in another interaction. Along the way, its direction may change through curvature, its frequency may change through gravity or expansion, and its quantum state may spread across several possible paths. It may be delayed relative to another route, lensed into several images, or stretched until its original color is no longer visible. Still, in vacuum, every local observer measures it moving at the same invariant speed. This constancy holds while almost everything else in the description becomes relative. The final mystery is not that light experiences eternity in an instant, because experience is not a concept physics can assign to a photon. The mystery is that the geometry of reality permits a path with vast separation in space and cosmic history, yet no proper time along the route itself. Emission and absorption stand apart for the universe and touch along the null structure of space-time. Light does not merely travel through reality, it defines the causal framework by which reality is connected. Every distant image is an intersection between two events, one in which matter releases energy into the electromagnetic field, and another in which matter receives it. Between them lies a path that can cross the age of stars without carrying its own clock. The photon begins as a quantum change, moves according to wave-like amplitudes and relativistic geometry, and ends as another quantum change. Particle, wave, and field are not rival stories but partial views of this single process. The deeper answer to how light works is therefore not a picture of a tiny object rushing through emptiness. It is a union of quantum exchange and space-time structure, where energy comes in indivisible amounts, possibilities interfere, and distance can remain immense while proper time vanishes.